Greetings and welcome to our team's presentation on this aerial firefighting vehicle that we have designed. We hope that by the end of the presentation, you will choose to invest with our company as we move into production. We're looking for a $5 million investment for a 10% stake of our company. I, Richard Gildard, will be presenting along with my co-founders, Ryan Smith, Michael Crump, and Meet Patel. Next slide, please. We all know that due to climate change, forest fires are becoming more severe and more common. The severity has been increasing and on an upward trend over the past several years now. And since 2006, the number of acres burned per fire has trended upwards. In fact, in 2020, over 10.2 million acres of land were consumed in forest fires. And that was the record set since 2000 when we started collecting this data. Next slide, please. A wide variety of aerial firefighting vehicles are used in industry today. They include helicopters such as the Chinook Heavy, a single engine air tanker such as the Air Tractor 802, scoopers such as the Viking CL415, large air tankers such as the Lockheed HC-130, and very large air tankers such as the Boeing 747. Most of these aircraft are older, retired military vehicles or converted commercial vehicles, and they were not designed for the intended purpose of firefighting, nor are they state-of-the-art for modern-day technology. Next slide, please. In 2020, the USDA produced a study that analyzed a variety of sources and vehicles that were used in aerial firefighting, and it was determined that helicopters, in fact, had the highest success rate in terms of their drops hitting their targets. Very large air tankers and large air tankers had a success rate around 70%. They were able to carry more water to the target, but had a lower chance of actually hitting their intended targets. Whereas helicopters, especially the heavy helicopters such as the Chinook, were able to get an on-target success rate of approximately 88%. Next slide, please.
Hello, I'm Michael Crump, and I'll be talking to you next about our requirements and customer needs. So as Richard mentioned, when we looked at the current available options on the market today, we took this idea of large capacity of retardant and high probability of success into our customer needs. We did a lot of market research, as you can tell, and we also analyzed extensively our customer operations, right? How firefighting works in this aerial domain and how the current systems that are on the market are used. From that, we created a core requirement summing up the mission. And from that core requirement, we're able to create sub-requirements that then informed further layers of requirements for our system. We created verifiable engineering characteristics from these requirements, prioritizing system utility and functionality, but also making sure to emphasize good human systems integration and sustainment as we move to field these aircraft. From there, we were able to refine the requirements. Once we selected an architecture, it really informed a lot of our engineering characteristics. And we ended up finding that our requirements were satisfied by just a few core subsystems and components, with everything else kind of surrounding that and enabling this. Next slide, please. So here's a bird's eye view of our requirements diagram. We're not going to dig too much into the weeds there, but you can see there at the very bottom, we did start with that core requirement. And you can see how it kind of spider webs out, and every layer adds a new kind of piece to the puzzle as we look a little bit deeper and try to figure out how we're going to enable this firefighting mission. Next slide.
Thank you, Michael. This is Richard Gildard again. I will be discussing the TOPSIS trade study that we performed on a variety of the specific vehicles that are currently being used in the aerial firefighting sphere. We looked at our customer requirements and our engineering requirements and tried to find as much as possible hard data to compare each of these aircraft to each other. We looked at specific high value targets such as carrying capacity for retardant, the price of the aircraft itself, as well as the loaded range, which would dictate mission space. In this, we found that the larger, very large air tankers and large air tankers such as the Lockheed C-130 were able to carry the most capacity of retardant and have the longest range, But again, their maneuverability, climb rate, turn radius, max maneuvering speed definitely took a hit being a fixed wing, larger aircraft as compared to the Boeing CH-47, also known as the Chinook, which had a very comparable carrying capacity in 3,000 gallons, but much improved climb radius and maneuvering capability. The only hit that the helicopter took was in range, as it was not able to carry enough fuel or travel fast enough to have quite the same mission scope as some of those fixed wing aircraft had. And going forward, we'll see how we try to resolve some of these conflicting, challenging problems that these aircraft ran into. Thank you. Next slide.
Thank you, Richard. This is Ryan Smith. I'll be going over the next few sections of our presentation, and starting with our concept of operations. Shown here is the general concept of operations for aerial firefighting vehicles. The concept of operations for our aircraft is very similar. It's been broken up into 9 stages, including the takeoff, climb, en route to fire, and then arriving at the fire and descending onto the fire. And then the next step would be to deliver the fire retardant and make as many rounds as needed to use up all of the fire retardant on board. And then the aircraft will depart from the wildfire, go en route to another station where it then descends and then reloads. That station could be the same station where it took off at, or it could be a station nearby that happens to be closer, or it could, even in the case of an amphibious aircraft, it could go onto a nearby body of water and refuel its fire retardant there with actual water from the environment. And that would be a faster way to go through the entire mission. As you can see in this concept of operations, we're tracking the altitude, temperature, and speed of the aircraft, as well as the total time for each stage. The number of minutes for an entire mission estimated here is around 190 minutes, which is a little bit over 3 hours. Thank you. Next slide. Okay, so once developing the concept of operations, we're able to create a functional decomposition for our aircraft design. Based off of our ConOps, we need to do these 10 main functions, including aviate, deliver fire retardant, shelter the crew, communicate data, generate energy, maintain the aircraft functionality, which is also tied into our customer needs for maintenance and operability. And then we have to navigate. This is tied into our customer requirement and engineering requirements for being able to operate the aircraft in IFR conditions. So our navigation tools need to be a little bit more robust than your typical passenger aircraft per se. And then, for example, and then our 8th main functional requirement would be deliver the electrical and hydraulic energy. This could be needed for all of the lights on board, all of the aircraft power electronics or flight electronics, and hydraulic energy for, say, actuators and any thing that needs to be opened or closed to deliver fire retardant. And then the 9th would be distributing fuel, and the 10th would be gathering wildfire information. So as you'll see, our one benefit our aircraft has over all the existing competition would be that we've integrated a wildfire detection system that will allow, using infrared cameras, pilots to actually see the location of the wildfire rather than having to guess based off of the smoke production. You see, since wind can change the location of the smoke as it rises in the air, the pilot can actually have a difficult time delivering fire retardant directly onto the wildfire. And they will also have a difficult time evaluating whether wildfire intensity has been reduced or the mission has been successful. So they might actually have to make multiple rounds before concluding that their mission had succeeded. Whereas if they're able to gather this wildfire data afterwards more accurately, they can more quickly evaluate the location and the success of their drops. So next slide, please. All right, so as mentioned previously in our TOPSIS analysis, we determined that the best option aircraft for probability of success for aircraft drop or for fire retardant drop was the Boeing Chinook. And then the best aircrafts for delivery of fire retardant in terms of sheer mass was the air tankers, specifically the large air tankers. So we wanted to develop an aircraft that is specifically designed for aerial firefighting that combines the best of these two options. So we came up with a quad tilt rotor design that has 4 wings and 4 engines that are fixed upright and then tilt down, sort of like the Osprey when en route to the fire. This aircraft can have very low stall speed, allowing it to more accurately deliver the fire retardant than, say, a Boeing 747. So it captures sort of the aspects of the Chinook and the air tanker all in one. Another aspect of this aircraft is that we are able to have a separate tank for dry fire retardant and water on board, so that the fire retardant will actually be mixed while en route to the wildfire and sent onto the wildfire during the delivery phase. And then when it goes to the next phases, the later phases in our ConOps, the aircraft can actually refuel the fire retardant and the water from a local, or it can refuel the water from a local body of water rather than having to go back to a base and refuel everything. So it has much more storage capacity for fire retardant than your typical Chinook, and it also has much more accuracy for the drop fire retardant drops than your typical air tanker. All right, thank you. Next slide, please. All right, and I'm going to hand this off to Michael, who'll go over some of our risk analysis for the project.
Thank you, Ryan. So when we talked about risk in this system, the conclusion that we came to is that operator error and environmental conditions cause a majority of our risk. We're asking our aircrew to perform very complex operations in a very complex aircraft under very complex environmental conditions. And when you add all that complexity together, you get a recipe for a lot of opportunities for things to go wrong. A couple of examples. In these high smoke environments, the pilot can easily become spatially disoriented. And that was a risk that we looked at very closely, as well as the risk of the pilot striking into an obstacle with one of the rotors while at low altitudes delivering fire retardant. Both of these are things that can be fixed by good human systems integration in the cockpit, the addition of visual and audio cues to alert the pilot when they're getting into unsafe conditions, and better engineering design to make sure they don't have to be in those conditions very long to begin with. Additionally, programmatic risk is also a concern. As with any new aircraft, there are substantial legal battles with the FAA in order to get certified for airworthiness. And then also large complex projects like this very typically run into issues with cost and schedule. So good program management techniques are at the heart of our mitigation strategy there. Having the appropriate subject matter experts in place and the appropriate personnel monitoring the situation very closely to make sure we're meeting our cost, schedule, and performance goals as we progress through each phase of the design lifecycle. Finally, some technical risk does remain. This is mostly due to the immaturity of the technology that we're using specifically for wildfire detection. It's very state-of-the-art, but we do expect that risk to diminish as the technology is given the chance to mature later down the line. Next slide, please.
Okay, so my name is Meet Patel, and I'm going to talk about system verification and validation. So we have identified total 23 different requirements that needs to be verified and validated, but I'm not going to go through all 23 of those. I'm just showing you some of the most important ones that needs to be verified prior to this aircraft being fully functional for these kind of missions. So there are top 7 requirements needs to be tested, and as we all know that flight tests are really expensive, so we can group all those 7 requirements can be tested in one flight test. So there are requirements such as the retardant drop rate success needs to be 70% or greater. That's something needs to have a flight test. The aircraft must have a fully loaded range of at least 200 nautical mile. The aircraft should be capable of piloted flight in both IFR and VFR conditions, and aircraft must possess the adequate performance and handling characteristic in this firefighting operation. The reason being that every time when you're trying to drop retardant in the site where you have fire, the aircraft needs to go in very lower altitude, and that's where your difficulty comes into play. So we need to make sure that the aircraft performs better in those lower level flights. So yeah, most of these requirements needs to be tested out in flight test. And I'm going to go to the next slide. And yeah, as we all know that due to climate change, there's increased number of fires in West Coast, and it's really causing a lot of danger. And right now, the aircraft that are being used for these firefighting operations are old commercial aircraft or old military aircraft that are converted into a firefighting aircraft. That's why we came up with a newer design where we selected a quad tilt rotor aircraft, which can carry more fuel for a longer mission, and it also has a capacity to carry higher amount of fire retardant, so it can perform multiple missions in one go. In order to make sure that this vehicle performs fine, we used MBSC to develop our vehicle. We also developed some parametric diagrams and instances to verify that the aircraft is capable of flying certain amount of range. It has enough amount of fuel on board, and so forth. The concept of operation was also developed, and risk management evaluation, verification, validation processes were also performed using the MBSC. So overall, we used we try to come up with a newer kind of aircraft to perform this mission. Hope you'll like our concept, and you may invest your money in our company. I appreciate your time. Thank you, everybody.